welcome to the April 2024 meeting, including first-time guests and new club members. If we have any new members or guests in the room with us, please feel free to introduce yourselves during our break after the presentation. For new members or guests joining us over Zoom, feel free to introduce yourself in the chat window. Please be respectful, and actually this says hold your questions until the end of the presentation, but Dr. Shull, our presenter today, said it's okay if you raise your hand and ask a question. For the audience in the room tonight, please, it says wait to ask your questions until the microphone is passed to you so that everyone on Zoom can hear you as well. And for the audience in the Zoom meeting, please put your questions in the chat window. We'll read them out for you. Okay, so Dana, you can go to the next slide. Okay, so safety slides. The first thing we want to do is identify room hazards. Some examples are the cables on the floor behind the projector. Dana has put a big rubber mat on top of those. There are some chairs with bags beside them. Low light or bright screen. We need to identify any CPR certified attendees. So you raise your hand if you're CPR certified. Okay, we have one gentleman up here and then Steve Blake in the back there. Okay. We need to designate an emergency caller. All right, Dana is our emergency caller. We can identify the location of the fire equipment, which Dana is pointing to in the back corner, back there. Is it in the kitchen, Dana, or is it outside the kitchen? It's right outside the kitchen. Okay. All right, cool. And then remote attendees, just please be aware of your surroundings. Here is our evacuation route. Obviously, in an emergency, exit via the stairs. Don't use the elevator. We are down here on the level A-level conference room. There are stairs out that way, down where all those chairs are stacked, and then there are stairs back that way behind the bathroom. Okay. So upcoming events, you can see these are color coded. The blue ones are outreach events. The yellow ones are like RAC regular events. And then the pink one here, I'll let Susan share about in just a moment here. So the upcoming events, just in sequential order, we have April 13th. That's tomorrow night. We have the Food Line Galaxy Nights in Sumter, South Carolina. April 17th, we have the Willard, which is our recurring event at the Willard Rooftop Lounge in downtown Raleigh. April 18th, we have our imaging meeting, and that one is our hybrid one. So it's going to be in person as well at the Cherry Building. The topic is 2024 eclipse images. April 25th, we have Githens Middle School STEAM Night. April 27th, Astronomy on Tap Star Party, which is in Cameron, I believe. Okay, I got a yes from Steve. May 3rd is our RAC observing session. Also May 3rd is First Fridays with TLC at Three Bears Acres, which is at one of our RAC Ob sites. May 4th will be a RAC class, but that topic has yet to be determined. And then May 8th through 12th is RACatoa, and I'll pass the mic to Susan in just a second to talk about that briefly. May 11th is the Art Space Galactic Family Day. May 16th is the imaging meeting, topic to be determined. May 17th, Prairie Ridge Eco Station Star Party. And May 24th is our next indoor meeting, How to Catch a Gravitational Wave. So Susan, if you wouldn't mind just saying a few words about what RACatoa is.
What exactly are, darn it. Okay, Raleigh Astronomy Club, astronomers with telescopes observing overnight, right? Overnight observe. Urban, I'm sorry. I love it, but I can't remember it. So anyway, we're getting together. Our registration is live on the calendar, so you can go and sign up. It's going to be the 8th through the 12th. You can come for one night. You can come for all 4 nights. If you, it's going to be at Staunton River. It should be just, it's going to be casual. We'll be providing some coffee, and I'll probably have some water for us all. There, you can camp on the, you can set your tent up on the field. If you're familiar with Staunton River, it's over by where the pool was, and they had the food set up. If you had just been to the Star Party in the spring or last fall, we're going to have that whole field. There will be some electricity. If you want to, if you have a small camper, you're welcome to park it in the parking lot, and you can camp there. The park asks for $25, which goes right to the park. We don't collect any money. You go right there, you pay them. It's for the one night or for the 4. There's bathrooms and showers available in the campground, and there's also bathrooms in the office. We're going to have just a lot of fun viewing. If you want to come and stay up all night and view, you've never been to an overnight viewing and you have no idea what to do, come over. We're going to be friendly. It's going to be very newbie friendly. And for the people that are real hardcore, we're just going to put you in a darker area. So if you have any questions, feel free. And if just come on up. And if the weather is going to be terrible, we will let you know, because we will cancel if the weather is like, you know, a terrible week. But if not, it's all good to go, and hope to see you there. Actually, they said $25 per astronomer. No, it's for the whole 4 days. Now, if you are coming and you like, we have two dogs. So we have actually made reservations in the campground, because with the dogs, you know, you don't want the dogs barking at you all night. So we're going to stay in the campground, which is, it's not that far. What is that, like quarter mile? Well, yeah, what is that? A half a mile, quarter mile? It's if that. It's not very far. It's a short distance. It's like walking from here to the parking lot. So it's not that far. So if you would like to, you can make a reservation and just pay the regular. Otherwise, everybody's going to be there it's $25. So, and the way I understood it is per astronomer. I know that if your family comes up or something for the day, we're not going to, if you have a guest, they're not going to charge. It's just, they want a head count, and that's the minimum that the park charges. So that's for the use of their electricity and their water and the showers and so on and so forth. So thank you.
Awesome. Thank you. And yeah, if you have any other questions, you can just email Susan or Dean, or you can also check the calendar. It's all up on there. There's a lot of information, an interactive map. There's all kinds of stuff up there. So, oh, and yeah, and Susan's email is on there as well. So you'll be able to find it there. Cool. Okay. So, typically at the end of an indoor meeting, we go out to eat. If you're interested in joining us, we have a few different options here, because we've had some feedback about wanting to try different places. We will revisit this after the presentation, and we'll actually like figure out what people prefer and how many people are going and things. So we can just skip this one for now. Just keep it in mind. So tonight's presentation is How Do Galaxies Grow and Evolve? And our presenter is Dr. Michael Shull. So I will first read the description that he provided. It says, the James Webb Space Telescope has made recent news with fascinating observations of distant galaxies whose sizes, shapes, and heavy element abundances puzzle many astronomers. Dr. Shull will discuss these observations and what they suggest about galaxy formation and evolution over the last 13 billion years. So our speaker, Dr. Michael Shull, is Professor of Astrophysics and past chair of the Department of Astrophysical and Planetary Sciences at the University of Colorado, Boulder. He received a BS in physics from Caltech and a Ph.D. in physics from Princeton University in 1976. After working as a researcher at UC Berkeley, he joined the CU faculty in fall of 1977. In 2019, he also became adjunct professor of physics and astronomy at the University of North Carolina, Chapel Hill. Dr. Shull's research is in theoretical astrophysics and space astronomy. His research interests include studies of gas between the stars and galaxies, exploding stars, supernovae, and galaxy formation. He has been a frequent user of the Hubble Space Telescope to study quasars, galaxies, and gas between the stars and galaxies. So without further ado, I will pass it over to Dr. Shull. We'll give him a second to switch presentations and we'll get going.
There we go. I think I am. Is it coming through? Yeah. I pushed the button. Okay. Well, thank you for coming. This is the third time I've spoken here, and I wanted to come up with something pretty recent. And so this topic caught my eye because there's been a lot of articles in the press about James Webb Space Telescope. It's now in its third year of operation. They just picked the third round of observing. Those of you know a little bit about it, I'm sure. It's 6.5 meters across, and it's got segmented hexagons. So it's not one big mirror, it's a bunch of small mirrors, all aligned very carefully. I got to see a lot of those because they built these out in Boulder at Ball Aerospace. And there was one time they were all in the clean room when we got to go out and see it. The way it operates, it points away from the sun and Earth out at the second Lagrangian point, and that big screen, looks like tennis courts, is the screen off the heat radiation from the sun and Earth, and it looks out the other way. So I'm going to call it JWST for short, James Webb Space Telescope. Something fun I learned after moving to North Carolina, James Webb is from North Carolina, and there's a high school up, I guess it's in the northeast part of the state, not too far from here, the James Webb High School. So he's a North Carolinian. Okay, so what the news reported, probably about a year ago, was meant to be, catch everyone's eye, and it did. The discovery of massive early galaxies, long, far away, distant galaxies. And they said they defied prior understanding of the universe. And these are little pictures of them. Those little red spots, those little fuzzy objects, are the very distant galaxies, almost 13 billion light years away, that they were talking about. And they showed up in these deep fields. So what was so strange about them? What was the problem? Well, a couple of my colleagues at CU Boulder were on that paper. Here's what the headline was. Erica Nelson said, "It's bananas." That caught the attention of the news. They said they found ancient galaxies, those little red fuzzballs, that shouldn't exist. Well, that's kind of an overstatement, but I'll tell you what they meant. Scientific American covered it, and I think they were a little more measured about what they said. I think they got it pretty much right. JWST's puzzling early galaxies don't break cosmology, is one of the claims was, but they do bend astrophysics. They challenge astrophysicists to figure out why they were the way they were observed. So what is the basic problem? In a nutshell, these are my words. These galaxies appear to be too massive, have too many stars in them at the early time after the Big Bang. This is very early times in the universe, about 500 or 600 million years after the Big Bang. And they have too few heavy elements, carbon, oxygen, iron, too few heavy elements for the number of stars that they made. Why is that a problem? Well, if they're too massive and they have too many stars, where are all the heavy elements that those stars made and blew out into space? So that was the basic problem. They weren't really breaking cosmology, but it posed a problem for how did these early galaxies grow so big, so fast, in so few years. In this next slide, which was a very serious paper that showed up in Nature magazine, I excerpted one slide so you can see visually what they were talking about. I'll point out that on the first line of authors, Erica Nelson and Catherine Seuss are both at University of Colorado Boulder, young assistant professors that were part of this team. So this is a plot of, on the vertical axis, the number of stars or the mass of stars. Now it's a logarithmic scale, so every one of those tick marks is a factor of 10. So you'll see I put in a dotted line there at 10 to the 10th, 10 billion solar masses. The Milky Way is several billion solar masses. And so those red dots are the galaxies that they found. They're as massive as the Milky Way, almost. Their masses are 10 billion, 10 to the 10th solar masses. And their redshift, if you know about redshift factors, on the horizontal axis, the redshifts are 6, 7, 8, 9. That is the look back time of maybe 12, 13 billion years ago, or certainly less than a billion years after the Big Bang. So as I said, and as Anastasia mentioned, it's okay if you have a question, stop me, raise your hand. I'd be glad to answer it while it's on your mind. Otherwise, you'll forget it and I won't either. Okay, so 13 billion years ago, something caused these galaxies to grow very large in a very short amount of time. And that was contrary to what standard simulations, theoretical models of the universe suggested. The other dots in this plot are many, many other galaxies at lower redshift. And you can see that they're way out there. These ones at the lower part, 10 to the 7th, 10 to the 8th, 10 to the 9th, those are dwarf galaxies, as I'll talk more about. So these are massive galaxies, as big as the Milky Way or Andromeda, first 600 million years. Okay, so it's good to show some pictures about present day galaxies. Yes, question?
You covered it already, but what function, oh, sorry,
Yeah, use the microphone.
what function, if any, does distance from here or anywhere have a role in there at all, or is it?
Yeah, this redshift factor, it's called Z, the letter Z, if you've heard of it. Astronomers will talk about redshift 1, 2, 3. When I was in grad school, redshift 4 was sort of the limit. But with telescopes getting bigger, we can now look farther away. The galaxies are farther away, higher redshift, and they're fainter. So the redshift limit now is up around 11 or 12. Okay, so if you take 1 plus the redshift, because redshift 0 is today, so 1 plus Z, you can turn that into an age of the universe or a look-back time. So at redshift 6, that's about 1 billion years after the Big Bang. If you go back to redshift 8, 9, 10, it's less than 1 billion, maybe 500 million. And the Big Bang, of course, is redshift infinity. So this scale gets squished very fast. Okay, so back to redshift 0, our local neck of the woods. The Milky Way, our galaxy, is a spiral galaxy, much like this one on the left. I'm going to talk about different types of galaxies, sizes, shapes, colors. The one on the right is an elliptical galaxy. There's also barred spirals and dwarf galaxies and irregulars. I'll show some of those. But what I'd like you to take away is that galaxies we can characterize by their size, their angular size or their physical size, their shape, are they a disk or a spiral, or they are elliptical, and their color. We're going to talk about red and blue and everything in between. So if you look at the one on the left, the spiral arms are red, not because the stars are red so much, but we're seeing hydrogen gas, a lot of the ionized gas around them. It's the H alpha Balmer line of hydrogen that makes them red. The interior is white or bluish. Over there on the right is an elliptical galaxy. Elliptical galaxies don't have many young stars. They don't have all those bright ionized gas around them. That largely explains the color. Okay, so I need to show this one plot because I'm going to use these terms red and blue. I already have red colors and blue colors. So over on the left is a plot of many thousands of galaxies schematically. And you can see along the top is called the red sequence. Those are galaxies that are pretty old. They're not actively forming stars. The stars are old. And they range from low luminosity to high luminosity. That's the red so-called quenched sequence of galaxies because they're not actively forming stars. At the bottom is the blue cloud. Those are very actively forming stars. Young stars have hot atmospheres. They're very blue, even ultraviolet. And then in between, what's in between blue and red? Well, they call it the green valley. But what I'm trying to show, which is on the left, is that when you plot their masses on the horizontal axis, that's another log scale, 10 to the 9th, 10 to the 10th, 10 to the 11th solar masses in stars. And on the vertical axis, you plot how actively they're forming stars, star formation rate. You can see that the active stars are all in that blue cloud. They're up there at very high star formation rates. The quenched stars, the old, red, and dead, are down at the bottom. They're non-star forming. So the takeaway from this plot, and this plot was a result of decades worth of observations. The takeaway is that if you're actively forming stars and building up your galaxy in mass, you're going to look blue, or at least in the rest frame, you're going to look blue. If the star formation has stopped or been quenched, so we call it, all those young blue stars fade away, they die, they blow up, and you're left with old stars like the sun, or even older than that, and they're red. So the color of the galaxy has a lot to do with its star formation rate. Okay, so how did we used to think, how do we once think galaxies formed? This talk is about how did galaxies form, and then how did they evolve? Well, gravity had a lot to do with it, and we still think that. Galaxy forms when the gas gets pulled in and the matter with it. The gas is mostly hydrogen and helium and a few heavier elements. And they were pulled together by gravity, and you see the sequence of formation. And if it's rotating, as it pulls in, it spins up like a figure skater pulling her arms in, or his arms in. And so that ends up collapsing to form a disk. And the bottom right shows a galaxy like ours, the Milky Way or Andromeda. It's a rapidly spinning disk that's flattened. And there's an instability of the disk that forms spiral arms. So galaxies like the Milky Way and Andromeda, which I'll show in a second, we thought form this way. What's new and different over the last 20 years is now we think dark matter, this invisible form of matter that we don't know what it's made of, but we can feel its gravity. And it's a lot more abundant than ordinary matter by a factor of 5 or 6. That dark matter is what really controls things. So if you're going to form a galaxy, somehow you have to do it first with the dark matter, and then the gas follows. Okay. Now, the second part of the talk is how do they evolve? So I put on one slide the main ingredients to galaxy evolution. In my course on galaxies, this would take a couple of weeks of lectures, but we're going to give a quick run through it. Stars are born and die over billions of years. The sun is going to live about 5 billion years, but the young massive stars only live 3, 4, 5 million years. So the more mass of the star, the shorter its life. Matter will continue to fall into galaxies because you can't turn off gravity. It keeps pulling matter in. And finally, a lot of the matter is in the shape of dwarf galaxies, and they're satellites. And I'll show some pictures that illustrate dwarf satellites and what's happening to them. So they get stripped as they fall in, and that's another source of matter that causes the galaxy to get bigger over time. But the most important fact that we've realized just in the last 4 or 5 years is known as feedback. It's the feedback of a star or a black hole on its environment. And we now know today that stars, after they die, blow up. Many of them blow up as supernova. But even while they're alive, they have stellar winds, and they blow matter off into space, and they have radiation that affects the surroundings. But the black holes, or AGN, active galactic nuclei, these are the quasars at the centers of most galaxies. They have a very powerful role as well. So collectively, stellar feedback and black hole feedback is the new ingredient that we think explains, or may explain, what James Webb saw. So gravity and matter falling in, and then this feedback, we think is the answer. So I'm going to tell you in the rest of the talk how this works and why we think it's going on. I want to show you one little cartoon that kind of illustrates how this acts at different mass scales. This is the distribution of galaxies in mass or luminosity. So on the horizontal axis, it's how luminous the galaxy is, but that's a proxy for how massive it is. The more stars there are, the more luminous it is, the more luminous the galaxy is. The vertical axis is called the luminosity function. It's just the distribution in mass or in luminosity. And the red line, which is the curved line going from the top left down to the bottom right, the curved line is what numerical simulations of dark matter tell you how matter should get distributed. And the way it works, and I'll show a movie of it in a minute, the way it works is the dark matter clumps up into little clumps. They're going to make lots and lots of satellites, lots and lots of dwarf galaxies, not Milky Way size, but dwarfs. And the Milky Way, I've put right there in the middle. We're sort of a middle-sized galaxy, about 3 × 10⁻⁻. So that's 30 billion times the luminosity of the sun, right in the middle there. And then up at where it falls off to the bottom right, those are the massive galaxies, or even groups of galaxies. So this is the distribution. The observations in blue don't look like that at all. The Milky Way is about right, but there are far fewer dwarf galaxies today than the models tell us. And there are also far fewer big galaxies, massive galaxies. So something is getting rid of them, or quenching them, suppressing them. And that's something we think is feedback. Joe Silk made this plot, so it's his sketches that we're showing here. So at the low mass end, at the dwarf galaxy end, that little squiggle up there, SN, supernovae, lots and lots of massive stars blowing up and blowing the matter out of the dwarf galaxies. That's the feedback process. So that's pretty well understood. If you have lots of supernova going off and there's still gas around in that dwarf galaxy, it's not going to stick around. The supernova energy just blows it away. So that is what makes that suppression at the low mass end. At the high mass end, it's AGN, active galactic nuclei, which is short for quasars and black holes. So the supermassive black hole at the center of most galaxies, including our own, is shown in the sketch there, where you've got accretion disks around the black hole and outflows or radio jets dumping energy into the galaxy that also suppresses star formation. But if you look at that little shell around there and little red stars, a quasar can also have positive, instead of suppressing the gas from forming stars, if it sweeps it up into a shell, maybe it can form new stars. And that's the key to solving the James Webb problem. So, okay, I've given the end of the talk first, and now we're going to circle back and talk a little more how that really happened. The answer seems to be that you get rid of the dwarf galaxies with supernova at the low end, and although you suppress some of the star formation at first, maybe after you sweep up the shells and compact the gas, you form lots of new stars, and that builds up the masses and explains the galaxies being too massive for what the model suggested. So that's where we are right now with our theories and observations. Let me now walk you through with some visual aids on how this seems to work. There's lots of satellites. I told you that dwarf galaxies are swarming around the Milky Way and Andromeda. This is just a schematic of showing you the streams of galaxies that have been found. And many galaxies around us have dwarf satellites. I'm going to show you some of them. The big galaxies also collide. I mean, gravity works on large scales. And these are two spiral galaxies passing through one another and creating a lot of activity. All the red light that you see are massive stars, probably triggered by this collision. And there's some in between as well. And here are my favorite with the tails, the tidal tails. These are called the antennae, but there's other pairs that we've found. These are two spiral galaxies that are on their first passage. And the way gravity works, just like it does on Earth, tides are on both sides of the Earth. It pulls harder on the near side than on the far side. So you get a bridge in between, and then these long tidal tails going off to the side. And then finally, in addition to the galaxies getting stripped and falling in, there's a lot of gas falling into our Milky Way that continues to give fuel for new stars. These are the so-called high velocity clouds. Those of you who know about the southern hemisphere, the Magellanic Clouds, I've labeled them, the large and small Magellanic Clouds. Gas is being stripped out of them, and so you can see that gas coming around in orange all the way around to the other side and up through the Milky Way. These are images taken in hydrogen, the atomic hydrogen 21 centimeter line, if you know about that. Anyway, it's a way that radio telescopes can image the gas stripped out of these galaxies. But everywhere else, you can see that orange or reddish hue. That's high velocity gas falling into the Milky Way disk from far out 30, 40, 50,000 light years. That gas falls in and it's fuel for new stars. So galaxies are getting bigger. This is something that I've worked on. Roughly 1 or 2 solar masses a year is falling into the Milky Way. Doesn't sound like much, but over 1 billion years, that's 2 or 3 billion solar masses. That's a lot. So these high velocity clouds are falling in and making the Milky Way get bigger. Okay, so just a little bit to refresh your mind if you've seen this, bear with me. This is just to remind you that we live in a spiral galaxy at the center of this plot, but out in the halo are many, many satellites, probably 30 or 40 of them, just around the Milky Way. They're in the lower left of the Magellanic Clouds, which are out at 162,000 light years or 200,000 light years. But there are others even farther out, and I've labeled them around. These are all bound to the Milky Way, and many of them are in orbits orbiting around that will eventually spiral in. Give them a few billion years. And we're in what's called the local group. So in this picture, the Milky Way is there at the center. We shouldn't be at the center really, but this is where the artist put us. If you look at the lower part, over to the lower right, that's Andromeda, M31, our neighbor. It's actually a little bit bigger than the Milky Way. They're both of order 1 trillion solar masses, 1 or 2 trillion. It's about 2.5 million light years away. We're bound to each other. We're falling together. And in about 3.5 billion years, Andromeda and Milky Way are going to pass through each other. I'd love to be there and watch what happens. Nothing is going to hit physically, but we're going to pass through, and all the stars are going to get shaken up, and some are going to get stripped out, and it's going to look like that galaxy collision I showed you. There's a third spiral galaxy that I've labeled M33. Those of you who are amateur night sky viewers know it well, I'm sure. A little bit farther away. It appears to be tangled up with Andromeda. It may even be bound to Andromeda. They're doing a little dance. So all those are going to pass together in 3 or 4 billion years and make a much bigger single galaxy. But each of these 2 galaxies have satellites around them that continue to make them grow. So the Milky Way is about 1.5 trillion solar masses, Andromeda maybe 1.8 trillion. When they merge together, you're going to have something that's about 3 trillion solar masses. And then there's a lot of other matter around that we haven't fully accounted for, including dark matter. And all that stuff is going to merge together into one super galaxy. Come back in 5 billion years and see if that's right. So we're all growing. Every large galaxy here is gaining mass because of this effect of gravity. Okay, I've talked a lot about Andromeda. There it is, 2.5 million light years away. It's very blue in this picture. Those are the young stars out on the spiral arms. The inner part, the bulge, is reddish. Not much star formation going on except in the very center. And it's got many, many satellites, but the 2 big ones, M32, also a Messier object up there on the top left, and NGC 205. Those are both orbiting Andromeda and will eventually spiral in. There's a frictional force due to gravity that causes them to spiral in. So Andromeda is going to get bigger. These 2, which if you go to the southern hemisphere, are lovely objects to look at. The Large and Small Magellanic Cloud. One thing that's happened in the last 5 years is their masses have gotten bigger, not because they've grown. It's just the way astronomers measured them has changed. And we now think the LMC is close to 10%, maybe even a little more, the mass of the Milky Way. And it's tied up with the Small Magellanic Cloud. These are very active star-forming galaxies. They're very blue, lots of massive stars in them. And they're in our halo, about 200,000 light years out, but they are slowly spiraling in. They will eventually spiral in. And the dwarf galaxy, I mentioned Leo in that previous one. This one is way out in the galactic halo. 250 kiloparsecs, 815,000 light years. And it's near Regulus. So if you're looking for it, you've got to make sure you block out Regulus. But it's got, I don't know, several million stars. And I'm going to go back just to show you, remind you where it is in this picture. There it is, labeled up on the top left. It's way out in the halo of the Milky Way. It's falling inward. We think it's bound. And using the laws, Newton's laws of gravity, that's one of the ways we measure the mass of the Milky Way, because its gravity is influenced by everything inside its orbit. And so we think it's about 1.5 trillion solar masses of gravity around the Milky Way. So that's Leo 1. Okay, now back to the theory that that I told you predicted that these galaxies that James Webb saw shouldn't be there. So let me walk you through the numerical simulations, we call it. These are supercomputer simulations on the world's largest computers, and you run them for literally days to run the universe back from the beginning all the way to the today. What we find in these simulations is that the galaxies form where this cosmic web of dark matter intersects, where the filaments intersect. So you can see the cosmic web. It looks like a big spider web. How does that happen? Why does it form a spider web? Well, I'm going to use my hands to kind of illustrate what happens. Gravity, as you know, pulls hardest on things close by. So if you have something that's completely round, spherical, it would pull everything in symmetrically. But matter isn't round. It's not spherical. And just a little bit of out of roundness, flattening into an elliptical shape, means that the short axis is going to collapse first because it's closest to the center. So nature, gravity, pulls hardest on the elliptical short axis and makes it flattened into a pancake. And then the pancake, if you look at it, isn't round either. And it pulls that in and makes a filament or a rope. So all these rope-like structures are formed by just gravitational forces, pulling things that are slightly out of round into the spider web. And then where the web crosses, where the filaments cross, you can see all the bright orange spots. That's where the gas falls into the dark matter and collapses and forms stars and galaxies. So if I could just say it in a nutshell, the matter follows the dark matter. The ordinary matter, hydrogen and helium gas, just goes where the dark matter tells it to go, which is into the cosmic web. So you can program the computer to form galaxies, form stars, let them live and die, run it for days, weeks, and it will tell you the sizes and shapes. And you can see already there's lots and lots of little black dots, and then some orange dots that are a little bit bigger, and then just a few of the very large galaxies. I count 1, 2, 3, 4, 5. So most of the galaxies in this picture are small dwarf galaxies, but then they merge together, kind of swarm together. They're pulled in by gravity and they form the bigger galaxies. So if you zoom in on one of those large galaxies, this is what it looks like. And that is going to turn into a very large cluster of galaxies with lots and lots of satellites. Every one of those little red dots is a mini halo of dark matter. Now, not all of those are going to form stars because the gas is going to get blown out and not held onto. But the ones that are kind of bright, you can see, are forming stars. Then you turn on the feedback. So I'm going to tell you in one slide, once again, to remind you what we mean by feedback. Question.
Previous slide, where was that from?
This is from a supercomputer calculation called Illustris. So if you, I think it's ILLUSTRIS out of Harvard. Our group has done similar ones at Colorado. You just Google numerical simulations or cosmological simulations and you'll find it.
Yeah, I got another question. The units right there, is that mega?
That's megaparsecs, 15.6 million parsecs. And the little h is a technical thing that depends on the Hubble constant because the distance
Okay, I was
scale.
like per hour. My
No,
God.
no, sorry. It depends on the Hubble constant. This calculation assumed a Hubble constant of 100. We know today it's more like 70, but that just sends the distance scale of the calculation. That's a technical point. Okay. So feedback. I said this before, but I'm going to say it again. Now you're paying attention because you know what feedback does. Feedback is what is going to suppress the star formation, stop the stars from forming. It comes in three types. There's radiative feedback. That's the ionizing photons, ultraviolet mostly, from the stars and quasars. That heats the gas and ionizes it, and then it blows out or drifts out of the dwarf galaxies. So radiative feedback helps kill off the small galaxies. Gas dynamical feedback, well, that's the exploding stars or supernovae, stellar winds, and quasars, which also blow matter out in what we call galactic winds. So if you expel the gas from the disk or the center of the galaxy, you're getting rid of the lifeblood of the galaxy. It no longer has the fuel to form new stars. So that's gas dynamical feedback. And then finally, this is kind of the new ingredient that goes into fixing the problem of James Webb. It's the plasma jets from the quasars. They inject relativistic plasma, gas moving near the speed of light, hence relativistic, into the galaxy halos and clusters. And then a parenthetical note, this is from me, editorial comment. Galaxy collisions also transform the shapes and strip away their gas, and that loses the fuel for star formation. So all of the above is going on, and collectively it's known as feedback. Feedback from the formation of stars, and feedback from the formation and feeding of black holes. So I can come back to this in the question period, but I'm going to move on to show you some pretty pictures and then wrap up. This is an example of feedback from an OB association, a small star cluster in the Large Magellanic Cloud. Anyone know what it is? Bingo, very good. The Tarantula Nebula. Also, well, it has technical names too, but it's colloquially known as the Tarantula Nebula because of all the legs and filaments. Right at the center of that bright star cluster in the Large Magellanic Cloud, when I was not in grad school, but a young assistant professor, some astronomers at Wisconsin thought they had measured the mass and thought it was a supermassive star, maybe even a black hole. It's not. When they looked at it with interferometry, that single object broke up into smaller 100 solar mass stars. So it's actually a star cluster of maybe 1,000 O-type stars, 50 to 100 solar mass each. And the ionizing radiation is blowing away the gas. All the red filaments are gas. It's the Balmer alpha line of hydrogen. So this is feedback at work. That star cluster is going to disrupt all the matter around it. And actually those stars eventually are going to lose their binding and they're going to dissipate as well. Same effect is going on in our Milky Way, in Orion, in the Carina Nebula. Most OB associations form like this, but then they die, they dissipate as they blow away the gas and lose their binding. This is an example of the AGN or quasar feedback mode. It's an optical image of the Hercules A galaxy at the center, and then superimposed is an image from radio, synchrotron radiation, energetic electrons spiraling around magnetic fields, but what you see is they come out in jets on both sides. And you track those back in, as radio interferometers do, they go right into the center of that galaxy where we think there's a supermassive black hole. And as you feed the black hole, it squirts matter out. If you feed it too fast, it squirts matter out both directions in jets. And this relativistic plasma is the feedback that was the bottom of my previous slide. That's the radio mode from quasars. This kind of thing is going on elsewhere, including our Milky Way. Now, our Milky Way at the very center of this image, these are galactic coordinates. So you can see the disk plane of the Milky Way. Right at the center, you can't see anything there, but if you look in the infrared or radio, there's Sagittarius A star, it's called. It's a supermassive black hole, about 4 million solar masses. And Andrea Ghez and Reinhard Genzel got the Nobel Prize for this a couple years ago for monitoring the stars orbiting around it and using laws of gravity to measure its mass. Well, we think that that supermassive black hole, which is dormant right now, wasn't always so quiet. If you look above and below, you see these bubbles, evidence for outflows. The Fermi Gamma Ray Telescope first found it, and then the E Rosita X-ray telescope tracked it. This is an X-ray image. And this gas is up at around, let me think, 8 kiloparsec, about 25,000 light years above the Milky Way disk. So it's blowing a lot of matter out. It's sweeping it up into a shell. The northern shell is bigger than the southern shell, maybe because the gas was a little more resistant on the south. We don't know. You can look over and see other evidences of feedback. The Magellanic Clouds are over in the lower right. Over here in the disk, the little green curved shape, that's Cygnus, the Cygnus region. Lots of massive stars there that are blowing up as supernova and a lot of stellar winds. There's an X-ray bubble over there. And there's other things in here. But the thing I wanted to illustrate here in the X-rays is that the quasar feedback is dominating for the Milky Way, or it was in the past. It's dormant today, but this kind of stuff may be like a volcano. It goes dormant, and then it becomes active again. Okay, so I want to show an image. I'll not click it yet. I'm going to show an image of this, another supercomputer calculation that shows you what the dark matter is doing. And watch it. It goes on for a minute or so. Watch everything kind of pull together and form clusters and galaxies, all due to gravity. There's no feedback in this model. And it's lighting up where the galaxies are. You can see the cosmic web. And the image is rotating so you can get a 3D picture of it. Right at the center is going to be a supercluster, a very large cluster. Here come all those satellites zooming in. And you can see every galaxy is getting bigger, but the one in the center is really getting bigger. But there's still a lot left over. So I'm going to go back and run it again. It's always good to see things the second time. And watch the filaments now, not just the center, but watch what's happening in the filaments. There's still galaxies forming out there in these distant filaments. The Milky Way would not be one of those going into the center. We would be out in one of the distant filaments. Our largest cluster is the Virgo cluster, which is about 50 million light years away. So we're still out in the suburbs.
So I got a quick question.
Yes.
So yeah, that simulation you just showed us, as far as that's just an arbitrary simulation. It doesn't represent it.
A pretty old one. I took it because it shows just the dark matter. Yeah.
So I mean, like what you were just saying, like when you're narrating, what we're seeing there wasn't actually like the Virgo cluster in the middle, or
No, it's arbitrary initial conditions, but you know, we always say this would be what a large cluster like Virgo or Coma would look like. If you go to more modern simulations, this is actually a very active diagnostic because there's information in the masses of the clusters themselves. They're not all the same. But this is a pretty typical one. It's going to end up being about 10 to the 15th. So 1,000 trillion solar masses. So 1,000 galaxies like the Milky Way went into forming that. And that's a pretty typical cluster. Okay, so back to the Milky Way. I like to say things a couple of times because then now you have the context. I told you that matter is still falling in to the Milky Way. So here's the Milky Way disk in optical light, even with the dust clouds in there. There's the Magellanic Clouds, LMC, SMC, with their distances in kiloparsecs. Very accurately known now because of eclipsing binaries. And then the stream, the so-called Magellanic Stream, hydrogen gas stripped out and going all the way around across the south galactic pole. So this gas is out in the halo, but it's going to fall in the Milky Way. It's low metallicity. It doesn't have a lot of heavy elements yet, but it will fall in and allow the Milky Way disk to continue to make stars. If we didn't have the infall of gas like this, our Milky Way would fade out. It would become one of those red and dead quenched galaxies I told you about at the beginning. But it's not. It's going to continue to form stars because of gas like this falling in. And this is going on elsewhere. These are also superposition of optical images of galaxies, all NGC catalog galaxies. And then the contours in white are contours of radio emission of hydrogen at 21 centimeter line that you've heard me talk about. The hydrogen atom has a spin flip, if you follow the physics of it, and it emits a line at 21 centimeters wavelength, right in the microwave radio. And it's a really good way, if you have a big interferometer, radio dishes, it's a good way of mapping out where the gas is. And you can see that in all cases, the gas is, you can see signs of it getting stripped out. These are galaxies in the Virgo cluster. So they're moving around through the cluster. Something, probably hot gas around this, is stripping it out. They're not colliding with other galaxies. We think it's what's called ram pressure stripping. As they move through the hot gas of the cluster, it's like a headwind blowing by you. It blows your hair back. It blows the hydrogen gas back. And this one at the bottom right is a really good example of that. So this is an example of a gas effect where you lose matter. The previous slide, gas was falling in. This is a case where you remove the lifeblood. These galaxies will eventually run out of gas, stop forming stars, become red and dead, or quenched, that red population. So I think this is the last slide. I want to wrap it up and then take questions. The people, and some of these are my colleagues at Boulder, Mitch Beagle, and people that distrusted the headlines that said cosmology is broken, we don't understand it. They thought, well, maybe we do understand it. And the title of their article, which came out a couple months ago in the Astrophysical Journal, was, which came first, supermassive black holes or galaxies? As you might guess, this is a chicken and the egg kind of question. More on that in a second. So in this image, this watercolor cartoon, redshift along the top, 5, 10, 15, that's going backward in time. So the Big Bang is way over here where I'm standing, redshift large. The first galaxies started forming around redshift 20 to 15. And so that's shown here, the first stars. And so the old model said, okay, feedback kicks in and those stars get stripped of their gas, and it makes it hard to build up the massive galaxies that they were seeing at redshift 10, 9, 10, 11. What they've added is a form of, they call it momentum-driven feedback, but it's nothing more than that supernova shell or a quasar-driven shell sweeping up gas around it, compressing it, and allowing it to form new stars. And so you can see in their little cartoon, they've got lots of little stars, little yellow stars, formed in the shell. Momentum-driven outflow means swept up and then to a shell. That's positive feedback. It's not destructive, it's constructive. So you build up the galaxies faster than they should have at redshift 10, and then much later, the negative feedback, the destructive feedback from massive stars, stellar winds, supernova, and quasars kicks in, and then life goes on. So they think that's the answer. The chicken and the egg issue, I'm going to close with, which came first, the black hole or the galaxy. There's an ongoing debate of how you form the first black holes. So it really is a chicken or egg issue. It could be that there's a way of forming black holes without forming stars. You just get direct collapse. And maybe every galaxy had a seed in it when it formed that turned into a supermassive black hole that then helped it create more stars through this positive feedback. That's still very speculative. It needs a lot of work to flesh out how that really works in practice. But at least we don't need to say that the universe was broken. And that's a good place to stop and take your questions. Thanks. So take a microphone if you have a question. And
Hi. A question about when the large Magellanic Cloud and the small Magellanic Cloud have these filaments of gas coming off. Is it hypothesized that is also whatever their halo of dark matter is around them, or their filaments of dark matter interacting between them and the Milky Way?
as far as we can tell, both these satellites must be bound by dark matter, probably in the 5-to-1 ratio, five dark matter, 1 ordinary matter. But they're both getting stripped, and we can see that gas coming off. We can measure it in emission and in absorption. So the gas is getting stripped off. They're getting lighter. But what we have not seen, as far as I know, we have not seen the stars that should be there. They're pretty far away. So the stars have not been found in the stream. Many of the other streams around our Milky Way, the tidal streams, they've seen them in stars.
Does the dark matter flow like in the same way that stream of
Well, the dark matter should, we don't know what it's made of, but if it's a particle, which is the best candidate, it should obey the same laws of gravity. After all, we invented it because we need something to hold on to stars. So it should go out, but maybe not exactly the same way the gas does, because the dark matter won't experience the drag force that a gas will. And it's sort of like a comet. A comet has 2 tails. Yeah, the dark matter tail probably would be different. If we could ever find a way to see dark matter, like if it annihilated and made gamma rays, and you could take an image, we could answer that question. But so far, we don't know what dark matter is, and we haven't seen it.
Thanks.
Okay. Well,
Anybody online?
does anybody online have any questions? Looks like it. All right. Well, I guess if no one has any questions online or in the room, I guess that's it. If we give our speaker a round of applause, please.
Thank you.
Well, we have one. Marsha. Hey,
Did you put it in the chat box?
yeah, he's putting it in the chat box. Or unless Marshall, if you want to unmute yourself, that's also fine. A wild type of question.
Hey, sorry, can you hear me?
Yeah, that's much better.
Yeah. I was just wondering, the previous image to this one, it was a composite I believe X-ray. Yeah, this one, X-ray and radio, I believe. What were the observatories that were used for this data?
Okay, it's the radio jets. I'm pretty sure were the VLA, the Very Large Array Interferometer down in New Mexico. And I think Fraser Owen probably gets the credit for it. He's a colleague of mine. The purple, I'm not sure, but it probably, if it's the X-ray image superimposed on optical light, it's probably the Chandra. But it might,
Yeah, okay.
but it might be Rosette, the Röntgen satellite. I'm not sure on that. Sorry.
Okay, just curious.
Not
And
sure.
you said this was the Hercules A galaxy, is that right?
Hercules A. It's the center of the Hercules cluster.
Okay.
Yeah, but there's a similar one, Centaurus A. Cen A has similar twin beam radio jets.
Very cool.
There's a
Thank
lot.
you.
What's interesting about this one is that the jet, which starts out very narrow and collimated, ends up much, like a lollipop out at the end.
Yeah, very
That's where it
diffuse. Yeah.
stops. It fans out, and there's shock waves going on out there.
Awesome. Thank you.
And then that's it.
Gina online asks, will we get a copy of these slides? Do you have these slides publicly available anywhere?
I don't. I put this talk together myself. If you Google, the internet, you can find things like this. This is the Tarantula Nebula, but a lot of these are my own slides.
Cool. All right. Well, I guess if no one else has any questions, I think Dr. Shull deserves a third round of applause.
That was enough.